Hey, I'm Agent Crow, and today I will be trying to make a tutorial where we make this scene in Shadatoy. First, what you want to do is open up a new Shadatoy page. I want to try and show you how ray merging is done. So, let's say we have our camera, and then we have a couple spheres. These spheres will be approximated by a signed distance function. Basically, you pass in a point, and then it determines the distance from the point to the surface. The ones that we will be using today is a floor signed distance function and a sphere signed distance function. What you do is you have a ray direction. So let's say we're marching in the direction towards the sphere. You first calculate the signed distance function, so that's this distance. We can represent that as a circle around the camera. Pretend that's around this point. And then we march in that direction. Now we've hit the sphere. Technically we could do another march, but it's like going on until it hits something or within a certain range. So if this amount, this like distance amount, is less than a value, so we can do like 0.01, then we would render a color to the screen. But if it doesn't hit something, we calculate the nearest point. We march in a direction. This sign distance field is a safe march. You can march in any direction without hitting anything. This is sphere marching. Then we would calculate the sign distance again, march, calculate it again, march, again, march, and so on and so forth until you reach an upper limit of marches. And we don't hit the sphere. First, we need to set up parameters. We have to set up our coordinates, our screen coordinates, because currently we have normal UV. So if I output UV, UV.y, and then the color, this is 0, 0, 1 on the y, 1 on the x, 1, 1. So 1x and 1y. But we want to make this 0, 0 value in the center of the screen. So 0, 0 will be shooting the ray straight forward. That we can do by calculating a new vector 2 CUV, and that will equal UV times 2. Then we can minus vector 2, 1 0. So this right here will fill out the whole thing to be 1.0. You should probably have some knowledge of Shadatoy before doing this. Then if we output CUV, it should still be wrong because it's stretched vertically. So we gotta unstretch it. So times CUV.y times equals I resolution .y divided by x. So this is our aspect ratio. So it gets divided by its aspect ratio. And that looks correct. So 0, 0 will be in the center now instead of down here where we have UV. Then we have to set up our camera position. Oh, wait, forgot to make that a vector 2. Camera pose equals vector 3. I'm just going to have some values in it. Feel free to copy them. if you want the same scene, then I'm going to create then another vector 3. This has to be a vector 3, not a vector 2. We need to calculate the ray direction. So, in ray direction, we have to have a normalized CUV. So this is where we use CUV, and then forward, with whatever forward is. In this tutorial, the camera will always face the same direction. That, if you want that, let me know, and then I should be able to help with that. We also need an animated sphere pose, and then non-animated, because we want that circular motion in the spheres. So we can have two constants. We actually need to define more constants. So float, this will be sphere 1 radius equals 0.75. Vector 3, sphere 1 pose equal, well, we can set that in the main image. Then float, sphere 2 radius 2.75. We'll have them the same for both. Then vector 3, sphere 2 pose. Vector 3, 0.0. Now down here, if we want that animated sphere, like you saw in the preview, we can do sphere 1 pose. I'm gonna have it on 1 for some reason. Equals vector 3 sin I time. This is just a bunch of values that I found to work. You don't have to copy them if you don't want to. Just enter some values that are not the same as 0, 0, 0, 0. And I actually pretty sure I need to do that. Don't forget your semicolons. Now, we also have to define a vector 3 light pose, light position. This will be the direction where, or not direction, this will be the location which all the rays shoot to after they have hit something, to calculate, see if it's in shadow or not. I do not have soft shadows yet. We're just working on direct shadows, as if the light was an infinitely small point. So we can have this be vector 3. Now we need a new value. We can actually make this a constant, like a predefined int, and this will be the number of steps that it takes before canceling the ray. That will be 3 steps. Both 300 by default. You can change that if you want, just higher equals more calculation. You have to make sure your normalize is a vector 3. I don't know why I skipped over that. Now, we still need to do some boring stuff. We have to have a map, which is like a list of spheres, or that will be how we put our two spheres together. And here's the explanation. We have a camera, and then we have two spheres and the floor. The map will always contain the min. So if we calculate from this point the minimum distance, so it calculates all three, the distance of the closest of all three, and we can march in any direction by that amount. Same amount. Then it takes this new point, calculates the min in all directions, then merges the closest distance. So this was a perfect sphere, this was the closest value, and we can merge in that direction safely. That's what the map is. So we need two signed distance functions. First, float. This is the distance value. This is the distance between the waypoint and the closest pixel or area coordinate of the sphere. So we can call this sphere SDF signed distance function. We take in a vector 3 waypoint. This is actually I'll name it waypoint pose. Then we can have a float. No, vector 3. This will be the center of sphere. Then another float, and this will be the radius. This is the function for the sphere. I did not make this up. This is just what I found works, because a lot of this has been done before, and it's easier just to use the math that has been done before instead of making it up yourself. And then we can also make our float floor. That's the vector 3 ray point, or ray pose. I keep on calling it point. Then we need a float floor height. And we also need to define a floor height up here. Float. So we can have this as negative 2.75, and the floor SDF will be return ray pose dot y minus floor height. Now we have to make our map. This will return a distance. So float map, we call it map, and then it'll take in a vector 3 ray pose position. This will take the min of all the values. So we can have distance 1 equals sphere SDF. Then we put in our ray pose. We put in our center, which I'm just going to call up here. And then we also put in our radius. Now we can have distance 2 equals the same thing, but replace it with sphere 2. And then distance 3 equals floor SDF ray pose. Then we can put in our floor height. Now we want to take the min of all the values. So make min of D1 and the min of D1 and D2. So this should what? Return, if I can spell it right. Oh. Oops, that's my fault. Float, you have to make sure you assign. There we go. Yep, everything works. Now we get into the fun stuff. Actually, no, we don't. There's one more helper function that I 100% did not make up, because I could never make this math. But I'm just going to copy it over. And then we can replace the... All of this will be down in the description. You can find this tutorial shader linked in the description. So if you need this to copy this, or you could copy it from the video, that is fine by me, but I did not make this up. Do not blame me if it doesn't work because this is the same one I copied. Now we can get up into the fun stuff. So we need to. This is our wayMarch function. It will return a distance traveled. So this will be the distance from the camera to wherever it hit or ended. We will call this function wayMarch. We will pass in a vector3 camera position. Wait, no, pose. Vector3, then a way direction, and an int number of steps. Or we could just simplify it to steps. We initialize the distance traveled variable. It will default to 0. Then for int I equals 0, I is less than steps. I'm going slow. Then we add 1 to I. So this will loop over all the steps, if you haven't realized already. Then we make a new waypoint, or wayPose position. And then we do camera pose plus distance traveled times ray direction. This will march the ray in the direction that the ray is pointing. Or sphere marching, I mean. Sphere marching and ray marching are two different things. Sphere marching is what we're doing now, where we have our camera, and we have a signed distance field, and it will march to the closest point multiple times up until there. But normal ray marching will march a fixed distance up until, and it will just go through it. It will ignore it. It has no, as far as I'm aware, it does not know the sphere exists unless you give it parameters to mess with the sphere. This fixed distance ray marching is great for volumetric stuff, like atmospheres and clouds, which I'm currently learning how to do because I really want to, but can't figure it out. Now that we're marching in the direction of the object, actually, this is a little bit complicated to explain right now. We just have to add more code than I can explain. So we get a new flow, distance to object. This will get the closest object in the scene or point on an object equals our map. Remember, this returns the minimum distance of all the objects in our scene. Then we will pass in our waypoint or wayPose. Now we will set our limit 0.01. Well, actually, no. Oh, this is when it hits an object. So this is our lower limit if it's super close up to the object. And we will break from there. Distance traveled equals distance to object. So this will march, and the next step, this will march the distance to object amount, because this is how we're doing it up here. Now if distance traveled, don't know, is greater than 1000, so this is our upper limit, it will break out. I like to put the semicolons just to clean it up. Then at the end of this, it will return distance traveled. So this is our full rematch function that we will call in our get light and stuff. Back down here, we can make a new. Oh wait, no, after. We can make a new float. The distance traveled for each ray, because I'm pretty sure this is a fragment, and this will run on every pixel on the screen. So this is going to return a distance traveled for each pixel on the screen, which is what we're doing for the center UV coordinates. We will call the RayMarch function. We will pass in our camera pose, our ray direction, and the number of steps, which is what we called up here. I'm pretty sure we can just return distance traveled. I'm gonna try that. I have not tried it yet. So you see this line right here? You're supposed to put a plus equals. That's all. Okay. I just mistyped. Oops. But now we're back on track, and we can start calculating the lighting, because this is what you should see, and remember to multiply it by a really small value. Or decently small, not too small, because you just get white if it's too small, not too large, because you also get white. So somewhere in the middle should be good, like 0.2, no, 0.1. There we go. So just play around if you want that, and then we can see the second sphere, or first sphere, orbiting around the first one. Not really orbiting. I wonder if I can do that one day. Alright, we can start calculating the light. This... Further on we get, the less I understand it, but I decently understand the lighting. So we'll return a diffuse value. We pass in a vector 3 ray point, or ray pose. And we will also pass in a vector 3 light pose. Now we get the light direction. So from the ray position to the light direction, or light position. So to do that, we get light direction equals normalize. We have to normalize the value of light pose minus the ray pose. It is our light direction. Then we have to calculate the normal. That's this function up here. Normal equals calc normal. I'm pretty sure there's some fun stuff we could do with the normal. Ray pose. Now we calculate the diffuse. This is my short explanation of it. For those of you that are just like me. So let's say we have two beams of light hitting a plane. So one's going to be straight up and down, and one's going to be at a very shallow angle. Let's zoom in on the very up and down light. The light that hits the surface is relatively even. Like, it's concentrated in this one spot. But the same light on the angled one is like getting spread out over a large area. So that light gets spread over the whole thing. That's supposed to be what the diffuse light. So this is dimmer than the straight up and down light, even though these are the same width of light. It's just this is at the higher angle, so this is brighter than this one. That's what I understand it as. So we gotta calculate that diffuse. So this will equal clamp of the dot product of normal to the light direction. And then we have values. So this is our clamping value. Then we calculate the shadow distance. So shadow distance equals the ray march. So we're going to call this ray march function to ray march towards the light. We call it by doing ray position. So we're not starting from. You know what? We can change this. We're gonna change this to ray or there. So we need to calculate our ray origin. This is where we're starting the ray from, and we need to shoot that from the normal. Plus normal times a small value. So we're just doing it just above the surface. Times 2.0. I don't really understand the 2.0 because that was just on the site. They never explained it, so I don't know. Then we shoot it towards the light direction, and we add our steps value. Now if shadow distance is great or less than length of light pose minus ray pose, we make the diffuse. This is basically our shadow value. Times equals 0.1. So we're making it really dark. Really, really dark. And the shadow reduce the brightness. And then at the end, we just return the diffuse. If I compile it, it should ray position. Then at the end, we just have to do a few more calculations and this should be right. So we need to calculate the hit point of all the surface. So we need, if it hits here, we need to calculate the point. This will be vector 3 ray point or ray position equals camera pose plus ray direction times distance traveled. Then we calculate our lighting. So float lighting equals get light ray point or ray pose. Then we do our light pose. Now vector 3 color equals vector 3 lighting, and then we can return color. Boom. Done. So you now have a fully working custom ray marching shader. And see you guys next time. Bye bye. Like and subscribe because that's a normal thing to say now.